Okay, Algebra 2, let's talk about the remainder theorem. Oops. We spent a lot of time talking about remainders. Now let's talk about what we can do with that information. And we're going to actually start out with some exercises. Consider the polynomial function. First, we're going to divide that function by x minus 2. You're going to divide that function in the way that you like to the best. I'm going to divide that function using long division, because it is, in fact, my favorite method. Let's see, 3x, and that'd be minus 6x, subtract, gives us 14x minus 4, 14x minus 28, subtract, and I'm left with positive 24. So my answer is 3x plus 14 plus 24 over x minus 2. That's my remainder. Okay, now find the function evaluated at 2. F of 2 equals 3 times 2 squared plus 8 times 2 minus 4. So 3 times 4 is 12 plus 16 minus 4. 12 plus 16 is 38. No, 28 minus 4 is, in fact, 24. I'm going to point this out to you, and we will talk about it in a little bit. Okay, consider the polynomial g of x, and then divide g of x by x plus 1. Okay, you could fast forward this if you've got division. I can't read what I've written there. To the third power minus 3x squared, there we go, plus 6x plus 8. Right, so I have, oh goodness, x squared. That gives me x cubed plus x squared, negative 4x squared plus 6x. Subtract 4x up here. Minus 4x squared minus 4x. 10x plus 8. 10x plus 10, negative 2. So my answer is x squared minus 4x plus 10 minus 2 over x plus 1. Now I'm going to evaluate at negative 1. Negative 1, that's messy. To the third power, minus 3 times negative 1 squared plus 6 times negative 1 plus 8 gives me negative 1 minus 3 minus 6 plus 8. 6, 7, 8, 9, 10. Negative 2. So pointing out a pattern. Last one. Okay, we're not going to divide this one out. We're going to say, I don't know why I'm in red, I'm sorry, h of x divided by x minus 3 with the long division gives us the answer, x squared plus 3x plus 11 plus 30 over x minus 3. Can you guess what the answer to part B is? We're still going to do that one. We're evaluating it at 3, so 3 cubed plus 2 times 3 minus 3 gives me 3 times 3 is 9 times 3 is 27 plus 6 minus 3 is in fact 30. Very cool. Okay, discussion. So we did f of 2 and we got 24. We did g of -1 and we got -2. This is all on your paper in front of you. H of 3 and we got 30. We found the remainder when we did our division was the same as each function evaluated at that number, right? Stating it in more general terms, we suspect the connection between the remainder and dividing the polynomial. So we divided the polynomial by x minus a. We'll say p of x over x minus a. And we evaluated the remainder at a, we evaluated the polynomial at a, and as an answer, got the remainder. Where did we get this from? Well, if you look, you set x minus a equal to 0. That is what we are plugging in to evaluate the polynomial, right? So like the first one, we divided f of x over x minus 2. And then we evaluated the function at 2. That would be x minus 2 equals 0, x equals 2. That's what we plugged in there. And we got for our answer the remainder. That worked for all of them. Go back and look at your work, and you'll see that this is your x minus a. So x minus 3, we plugged in 3. X plus 1, we plugged -1. X minus 2, we plugged in 2. Works for all of them, right? One more thing. Excuse me. Going back to f of x. The first one we divided by x minus 2. So take your polynomial. There we go. 3x squared. I don't know why my pen isn't working. 3x squared plus 8x minus 4. We divided it by x minus 2. And we got 3x. Let's try something else. 3x plus 14 plus 24 over x minus 2. So if we multiply both sides of the equation by x minus 2, so we are rewriting f. Multiply both sides of the equation by x minus 2, and we get f of x equals 3x squared plus 8x minus 4 times x minus 2 plus 24. Okay, hold on a second. We're multiplying both sides of this by x minus 2. So multiply that times x minus 2 and multiply this side, all of it, by x minus 2. Okay, that's what cancels out that one. Okay, this right here is the remainder theorem. And we'll get into what we can actually do with that in a minute. Okay, this is what we just did. The remainder theorem. Let p be a polynomial function in x, and let a be any real number. Then there exists a unique polynomial function q, such that the equation p of x equals q of x times x minus a plus p of a. And it's true for all x. Okay, when a polynomial is divided by x minus a, the remainder is the value of the polynomial evaluated at A. Okay, let's have some fun with that. Exercises 4 through 6. Consider the polynomial p of x equals x cubed plus x plus kx squared plus x plus 6. Find the value of k so that x plus 1 is a factor of p. What in the world? Well, all we're doing is, okay, it's important to know that in order for this to be a factor of the polynomial, our remainder has to equal 0. Okay, so since x plus 1, we solve that for x equals -1, we must have p of -1 equals -1 cubed plus k times -1 squared plus -1 plus 6. So this is -1 plus k minus 1 plus 6 equals, let's see, k plus 4. Sorry, there's a 0 here. So k equals -4. Cool. Find the other two factors of p for the value of k found in part A. So we know that p of x equals x plus 1, because the remainder is 0, we know that that is a factor of the problem. So we need to figure out the rest of the polynomial. The only way I know to do that is to do some long division. If you have a better way, love to hear it. So we know this is x cubed minus 4x squared plus x plus 6. X squared plus x squared, subtract, I get 5x squared, so minus 5x, negative 5x squared, oh I forgot to carry down my x, minus 5x gives me plus 6, x plus 6, which is good. I need no remainders. So if I put this right here, this is what I need to work on. That trinomial at the end, I should be able to factor. So I have x plus 1, and that would factor into, like, factors of 6 are 2 and 3. So I need x minus 2 and x minus 3. Okay, so there's our answer, the other two factors. Okay, a little bit of discussion for that one. So remember, for any polynomial function p and real number a, we can say that q of x, the quotient, times x minus a plus p of a. The remainder theorem says that there exists a polynomial q such that all of this. Okay, but what does it mean if a is a 0 of p? Okay, that means that there is no remainder. That means that this is in fact 0. If a is a 0 of p, then there is no remainder. That last term right here is actually 0. Okay? How does x minus a relate to p? if a is a 0. Okay? If a is a 0, that means that x minus a is a factor of the polynomial. Which we just modeled in the last example, right? A was a 0, therefore x minus a was a factor, and we used x minus a, we divided by x minus a for the polynomial to figure out what the other two factors were. Okay, we're going to get into the graphs of the polynomials in a second, but basically to graph it, we use the zeros. Okay, x minus a being one of them, so a would be one of the zeros. And I'll show you that when we get to the example. Okay, consider the polynomial p of x equals x to the 4th plus 3x cubed minus 28x squared minus 36x plus 144. Is 1 a 0 of the polynomial? So that means I'm going to plug 1 in. Let me get 1 plus 3 minus 28 minus 36 plus 144. Give me a second. 3 minus 28 minus 36 plus 144. So no, 1 is not a 0 of the polynomial. Is x plus 3 one of the factors of p? Well, let's see if negative 3 is a 0, right? That's how we'll know. Negative 3 to the 4th power plus 3 times negative 3 to the 3rd power minus 28 times negative 3 squared minus 36 times negative 3 plus 144. Okay, plug that into your calculator or do some mental math, and we see that we get 0 as an answer. So yes, x plus 3 is one of the factors of p. I think we're missing c. Hold on. Oh, the graph of p is shown to the right. What are the zeros of p? Here I have negative 6. 1, 2, 3. 2 and 4. Negative 6, negative 3, 2, and 4. So write an equation of p in factored form. I love these questions, as long as you can remember to flip your sign. Those are the best. Okay, we're definitely a 4th degree. All right, number 6. Consider the graph of a degree 5 polynomial shown to the right with x-intercepts given. Write a formula for the possible polynomial function that the graph represents using c as the constant factor. So first I'm going to read this, and I'm at, let's see, 1, 2, 3, 4. 1, 2, 3, 4, 5. Those look to be my zeros, so I need to write a function. P of x equals a constant term, x plus 4, x plus 2, x minus 1, x minus 3, x minus 5. Cool? So suppose the y-intercept is negative 4. find the value of c so that the graph of p has a y-intercept of -4. So that would be 0, -4. So, goodness, every time, right? That means p of 0 equals -4 equals c, so all of the x's are 0, do 4 times 2 times -1 times -3 times -5. Hold on a second. So -4 equals -120 times c. To positive c is 1/30. Seems really, really wrong, but it is in fact right. So let's write our equation. I have p of x equals 1/30 times x plus 4, x plus 2, x minus 1, x minus 3, and x minus 5. All done. Okay, let's discuss a little bit. What information from the graph was needed to write the equation? So we needed all of the x-intercepts to write all of our binomials, however many there were. Okay. Why would there be more than one polynomial function possible? Because the factors could be multiplied by any constant and still produce a graph with the same x-intercepts. Okay, we just did a p of x equals c times all of those binomials. Okay, our graph could be multiplied by any constant and still produce a graph with the same x-intercepts. Okay, that c is just going to change how it looks. You know, big curves versus little curves. That's wrong. You know, basically we still have the same zeros, just different amplified heights of your maximums and your minimums. But your zeros don't change. What else do I need to remember to tell you? Why can't we find the constant factor c just by knowing the zeros of the polynomial? Like we said, the zeros will stay constant, but the c changes sort of the amplification, how tall or how short the graph is. Even though it's still going to cross at the same zeros, the maximum and the minimum changes depending on the c value. Okay, lesson summary. Remainder theorem. We've talked about that one a few times. So what I want to point out is when a polynomial is divided by that binomial, the remainder is the value of the polynomial evaluated at a. Okay. Factor theorem. Let p be a polynomial function in x, and let a be any real number. If a is a 0 of p, then x minus a is a factor of p. Okay, and then there's two examples, but we worked through an example together also. All right, good job. One more thing I want to point out, sorry. Basically, just remember, if x minus a is a factor, then the number a is a 0. If p evaluated at a is 0, then x minus a is a factor. Cool, good work today. I think I already said that once. I just wanted to say one more thing.